there is a communication at a chemical level that happens when this connection or this glucose fits into that receptor. There is a communication that happens. It's got to travel into the nucleus, turn genes on, okay? And messenger RNA gets sent out, you got your whole transcription, translation that happens, and you end up with the production of insulin. Now, Danny, which cells?
Beta cells.
Good. Production of insulin. Insulin is then transported into our bloodstream. Kevin?
After that, it will travel in the bloodstream and fit into the insulin receptors.
Good. And what type of receptors?
Insulin receptors.
Good, yes. And this is, remember you were working on this. You remember we had that activity that we sent you out on your own and to see if you could figure out how it is that this connection works. I think we kind of had this sort of picture for you. Okay? How does that work? So insulin is now in our bloodstream, and just by a diffusion, you've got a high concentration of insulin in your blood, is going to diffuse into this little space right here. Refresh your memory. That is our extracellular fluid. This little region right here. This would have all of our ancient C components: water, sodium, potassium. Intracellular fluid. But this insulin cannot diffuse through our phospholipid bilayer. It works in receptors. So once the insulin fits into that receptor by a collision, it's going to set in motion. Again, there's going to be a communication, or this cell's going to respond to that interaction. And what's the next thing that happens? So I'll work through this row at the back now. So Quinton, what do your notes say? This I really want you to read from your notes.
It causes the vesicle to move to the phospholipid bilayer, and the glucose transporters are placed across the membrane.
Yes, absolutely. So vesicle would move. There'd be ATP used in quite a bit of ATP used in that movement. And these glucose transporters are placed into that phospholipid bilayer in the cell membrane. Okay, I'm going to show it with other cells that this happens in. What cell was this one?
Muscle.
Okay, this was the muscle. This is the pancreas. That was the adipose. Adipose or fat cell, yes. Which one was this? Was this brain we had? And then this was our liver. Okay, so you notice the liver is missing our insulin receptors, as well as the brain cells. Okay. So let's do this again for our, let's do our adipose cells. Same thing's going to happen. Insulin is going to fit into those receptors, sets in motion. The cell responds to this. Glucose transporters are placed in that cell membrane. So now our glucose can start entering into these cells. Interesting. No, yeah, go ahead.
Could this relate to why our muscle cells and fat cells find it a lot easier to grow when we have a lot of fat? Any relation? Because they have glucose or insulin receptors.
Muscle cells growing when we have lots of fat, or do
Yeah.
you just mean adipose cells growing?
Both in general, because carbs grow size.
Well, yeah, okay, that's a good point. Good question. Remind me about a good question, Craig. They're already behind the board and I just don't want to move it. Okay, so yeah, because this, I was going to ask you, what will happen to this glucose? What's going to happen to glucose? Some's going to be used for one certain thing, but the name kind of gives it away. Yep, Adele.
Wasn't that what I was asking? What happens to insulin after there's insulin receptors?
Yes, it would break down. Good job. That's another good question. Okay. 2 good questions. Remind me again when I pull this board back to give you guys good questions.
Can I answer that? It's stored as glycogen.
Try the language again. Can I help you out? Glycogen. Okay, I'm only showing you 2 spots where a major storage of glycogen occurs. So this is a good question for the class. There's 2 types of cells where we're going to find the most abundant concentration of glycogen. Okay, I'm going to ask for one and then give me another. Give me one. Yes, and give me the other one. Yes. In muscle and liver cells. So not in adipose. So let's keep working on what's going to happen to the glucose in adipose cells. Yeah, it's going to be used, like it's going to have mitochondria in there, and it's going to be used in cellular respiration. Do you remember, now I'm really going to push those neurons. In cellular respiration, we got to a molecule that I said this molecule can now go either into fat or into protein synthesis. It does not have to continue on into carbohydrate, complete aerobic respiration. Okay, I'm going to try Alex.
3PG.
I believe it was 3PG.
Are you ready?
No, did I say it was acetyl-CoA?
Oh.
Yeah, that's the one I chose. Yeah.
Yeah. You look at here's another, you got a busy night. You're looking at transport, I want you to go back and look at cell respiration where we talked about that. Acetyl-CoA.
Does it use the CoA when it goes for fat?
Acetyl-CoA, the CoA would help transport it
Oh.
into a place where it could be, go into fat metabolism or into protein synthesis. And vice versa, that from those fat molecules and from the protein molecules, you can generate acetyl-CoA to go into cell respiration. Okay. So it all depends. But yes, this is where you could end up having that glucose in a series of reactions becoming fat storage. It's important. Okay. It is important. Okay, and this guy, okay, our muscle cell, same thing. Our glucose would be first reaction hexokinase in our cell respiration, or it can be using enzymatic reactions. You can build your polysaccharide glycogen. At the liver level, we don't have to rely on insulin. This can be just continually diffusing in. Okay? Are these containers in the way that are no? Producing glycogen or going into cell respiration, generating ATP for all those cellular functions. Same thing with the brain. Your brain is just using your glucose so quickly. It's generating so much ATP that that glucose is mainly being used in cell respiration. Okay, well, because there was so much insulin in this blood, it's almost, we've got a situation here where we've diffused a ton of glucose into the cells. And we actually have a situation where we almost have too few glucose in our bloodstream. Okay. These guys will eventually break apart, our insulin. And when they do, these receptors are going to return back into those vesicles, and they're going to be removed from that surface. And glucose will no longer be able to be transported. In an ideal situation, so let's look at a nice, healthy diet. A diet of complex carbohydrates. Not a lot of monosaccharides, some oligosaccharides you can have. You can have some of your good polysaccharides. Starch is not necessarily a great thing, but some nice fibers, chitin, things like that. And what you would find, your blood would be in a nice balance. Now from the graph you looked at, is there ever a situation where you have more insulin than you do glucose?
Well, we did in the graph a little bit, it was like, it was at 9:30, there was a slight, increase, there was more insulin than glucose.
Ah, yes, a little wee tiny point, yes?
But other than that, it's usually.
In general, the insulin concentration is lower in your blood than glucose. That's probably a good thing.
And
The units are different.
yeah, it's different units. in the graph.
The one side is for the insulin and the other side is.
Yes,
So what's the difference between a
picomole, small,
It's even less.
even less.
So,
Yeah.
so then at no moment does.
Yes, at no moment, because of the units being different. Yes, thank you. Is it ever higher than your blood glucose? So we see there, this is a good situation that I'm seeing here. Some of the insulin, we'll put an insulin there. This one, let's put one in here too. We don't have a lot of insulin in the blood. So we have a nice, a good balance. You must maintain a certain concentration of glucose in the blood. You can never have no glucose in your blood. Can't. And it's mainly because of this guy. Yeah, it's not storing glucose. It is utilizing glucose that comes from the blood. So that glucose needs to be readily available. And if you decrease your glucose in your blood, you're going to run into problems. Low blood sugar.
Oh, is that why you?
Go ahead.
Is that why you faint if you have low blood sugar because your brain shuts down? It shuts down.
Yeah, you're trying to get right now. When you have a low blood sugar, I don't know whether actually fainting. If you get to a point of, I mean, fainting. The process of fainting is to get you on the ground so it's easier to transport stuff. So, in a really condensed version, if you're laying down, it's going to be easier for your blood to get to your brain because your brain is probably starving of glucose. Well, yeah, fainting is to get you on the ground so that you don't have to fight with gravity. Now, don't forget, fainting can come over a lot of chemical releases, right? Like a trauma or whatever might be happening. But typically, I mean, if really simplified, guys, it is to get you on the ground. That's why when you feel faint, what do they tell you to do? Lie on the ground. One of them is to protect yourself, because if you do faint, you don't want to fall crack.
So you head on the walking
And yeah, and the next thing is to help assist in that whole, whatever's going on internally to get the blood or the oxygen to your brain. Your brain is the #1 controller in this. So this is a nice balance. You don't want to go low. I want to show you now what happens is if you have this a low blood glucose situation. Okay, we're not gonna faint this poor person. Okay. Yes.
So the insulin receptor, the glucose receptor, when the glucose goes in there, can it just like send out one message, or can it stay there and like get more insulin made, or can only like use once?
Another good question. Okay, how many good question cards do we have here?
3.
3? Okay.
That's in my bag.
Can you remember how many A antigens were found on a red blood cell? Yes. Isn't this fun?
2. 1. 5,000.
Are you serious?
6.
Okay, who's got their blood typing lesson close by? Okay, Michelle has it, Sola has it. So, can you find it, please? How many antigens? No, you don't have it? Okay, Sola, we're relying on you. Danny?
Get it there.
Okay, how many hemoglobins are found in one red blood cell?
Oh.
6 million.
I don't know, 300,000.
50,000.
At least you got the million, right? Is it 200 to 300 million
Yeah,
What
okay.
am I-
Oh, yeah.
Wait, what am I finding?
in one red blood cell? Antigens, how many antigens typically are found, there, that's a lesson, are found on a red blood cell?
I have the
1.5 to 2 million.
1.5 to 2 million antigens, one cell.
See, I said 1 and 2.
How many glucose transporters do you think are on a pancreas? Let's guess 1 million, because we'd probably be pretty close, it might even be more, okay? So, glad you brought that up. This model does not do justice to how many proteins are found in a cell membrane. You gotta imagine there's 1 million of these are found responding to your blood glucose levels. Okay? Picture that? Same with the insulin receptors. Okay, so we have a situation here now where we have dropped our blood glucose levels. And I'm gonna say that this is not a great situation. This would be low blood sugar. You don't wanna do this. You do not wanna do this to your body. And by eating properly, you can minimize this from happening. You can't stop it. You're doing okay. You eat before. Okay. Okay, so what happens in this situation is that, and I'm not showing you the connection for this, so this is one of these, you're gonna have to trust me sort of thing. When blood glucose levels are low in our blood, there is a message that is sent to the pancreas. Same idea, but the trigger is not going to be on the alpha cells, it's going to be on the beta cells. Sorry, get it back. Alpha
Yeah,
cells.
because we already talked about the beta
Yeah.
cells. And if they
It's going to happen, you have to take that out.
So repeat it, so.
Okay, the trigger or the communication is going to happen to the alpha cells, not the beta cells. I'm not showing you the message. There would be a chemical, it's actually has to do a little bit with the lack of presence of insulin. Okay? Which I didn't show you in the beginning, I just showed you the presence of insulin. So you just have to trust me on this one. Okay, so we understand that whole interaction. There'd be a chemical signal sent, DNA, genes would get turned on, the DNA specifically would be in there, our alpha cells, transcription, translation, ribosomes are going to start producing a new type of hormone, whoopsie, called, that's a mutation. What's that called?
Please excuse this interruption.
This is
a
called
reminder to grade 10
glucagon.
teachers that tomorrow during period 1
Digimon.
please listen carefully to tomorrow's announcement.
Yeah, it's glucagon receptors.
Yeah, do you see it?
So it's going to make that instead.
Okay, so the pancreas is now going to exocytose glucagon. Glucagon is going to travel through our bloodstream. It's going to fit into the glucagon receptor, which is found at the liver.
How do you spell glucagon?
We got that on tape, just to let you know.
Yeah, oh.
We'll hold on, whatever. Okay, watch what happens here. This one I showed you more detail what's going to happen. Glucagon fits into the glucagon receptor. This enzyme gets released. Remember, our situation was low blood sugar. This is your body looking after this. This is actually kind of what you're doing at nighttime. Okay? It's going to now start breaking the bonds in glycogen.
What's the enzyme?
glycogenase.
It makes sense.
Sounds good.
Because of the names.
Why not? Let's make it.
Glycogenase, let's fire it up.
Miss Webb, does it send a signal to it, to the enzyme?
The enzyme is actually attached to the receptor, and it breaks off. Now, there is a few more reactions that happen between
Glucose
here.
receptors comes back out. The brain takes that. Right?
These glucose transporters can work both ways. Look what just happened.
Wait, what just happened?
Up to the brain, right?
Well, that makes sense.
We now found we more balanced our blood sugar.
Is that healthy, that process? Or no? You would want
Yes, it is. You have to have this.
half
Here's
of
the
it.
problem. The problem is when you do this sort of stuff. Oh my gosh. I ate, okay, here.
All the glucose.
I'm gonna eat a chocolate bar.
Brownies.
Your pancreas goes, beta cells go, "Wah, look at all this blood glucose. I gotta get so much insulin in there. Totally overshoots it. All the glucose, not all. So you go, oh, I feel so good. I'm so excited. I just ate that chocolate bar. now you go, oh. Your body goes, oh my gosh, look at the blood glucose levels. Fire up the glucagon. The liver says, I'll save you. But because it was so extreme, it overshoots it again,
Oh my god.
and it puts too much glucose.
How many cycles does it take? To
Ah.
Exactly.
You see that graph? Here's what you would like to do. You would like to eat a meal, and you'd like it to kind of do this.
Is that why it's healthier to eat
You
throughout
have
the
a
day?
chocolate bar, it does this.
Wait, why does it
Oh.
send out?
Okay, so, oh my gosh. Here's the problem. When you do this to your body, I know, where'd that go? When you do this to your body, those whole fluctuations, your receptors become intolerant to insulin. Okay? So you become, this is an insulin intolerance. Oh, that is type 2 diabetes.
That's the sesame seed.
That is type 2 diabetes. Okay, so I'd like you to make those notes on that page. And
I have one from history last semester.